Right, this video adds to the discussion of discrete random variables, and in this we're talking about means and variances for discrete random variables. And we've talked about mean, variance, and standard deviation before. But what changes here with the discrete random variable is probability gets introduced as part of the calculation that we're doing. So a quick reminder, a discrete random variable is a variable that has a countable number of possible values. Rolls of the dice, flips of the coin, number of red M&Ms in a handful that's pulled out of a bag, anything that we can describe as the number of, or maybe the amount of, right? Those might be considered discrete random variables. The word mean gets replaced with expected value sometimes. And if I asked you a simple question, what's the expected roll from two dice? I mean, what would you say? Because there are many combinations, anything from a 2 to a 12, but what's the expected roll? When we ask this in stats, we're really asking what's the mean of the discrete random variable for a roll of two dice. And if we roll two dice, these are all the possible outcomes here. What would you expect? Well, you might have said 7 because it's the most common roll, and maybe that makes intuitive sense. 2 is as common as 12. They sort of cancel each other out, and 7 ends up being the most common roll. So maybe that's what we should expect. Well, let's do a little math here. When we roll die, there are possible outcomes from 2 to 12, and they all have their own probability. And so when we talk about expected value here, we want to weight it based on probability somehow. So if we're going to talk about an expected outcome for 2 rolls of the die, we should weight it toward the more likely outcomes if we want to get a good sense for what we should expect. So the math is actually pretty straightforward. I'm going to take an outcome, we'll call that x, and then I'm going to take a probability for that outcome. And I'm going to multiply those, every outcome times its probability. And I'll do this quickly. 2 times the 136 is 236. 3 times 2 is 636. 1236. I'm measuring every outcome. I'm multiplying every outcome times its probability here. And we sort of get these weighted values, weighted based on probability. Finish these up here. When I multiply, I get that. 30 out of 36 for 10, 22 out of 36, and then 12 out of 36. So all these multiplications here result in the values I've calculated and so on. Now it turns out if I add all these together, if I take the sum of every outcome times its probability, what we get here when you add all these up is 252 out of 36. Add all these fractions up. And if you do that math, it turns out it's 7, which makes some intuitive sense. That's a weighted average. The outcomes are weighted by their probabilities. The expected value, or the mean, mu, of the random variable x, where x stands for a total of 2 dice rolls, is 7. Let's look at another example. Let's go back to Las Vegas. Let's look at a roulette wheel. A roulette wheel has 38 slots on it, 2 of which are green. And if you land on green, you automatically lose. The house gets your money. Vegas gets your money. Half the others are red, half the black. Let's say we're going to bet $10 on red. I might ask, what would you expect to win or lose? Negative winning would be losing on average here. And the idea, again, is to take every outcome and its probability. Well, it costs $10 to play, and if you win, you get $20 back, which means you win $10. So you bet $10 to win $10 net. So I might win, which is going to give me $10, but I also might lose, which is going to cost me $10. What are the probabilities? Well, there are 38 slots in the roulette wheel. 18 of those are winners. 20 of those are losers. Whoops. So there's 18 chances in 38 that I win, 20 chances in 38 that I lose. Let's do what we just did before. I'm going to weight every outcome by its probability, take each outcome times its probability. And if we were to do that in dollar form, 10 times 18 38s is $4.74. Negative 10 times 20 38s is negative 5.26. And if I add those together, I get negative 52 cents. That's the sum of every outcome times its probability. That's the expected value or the mean of the random variable x, which is the winnings on the roulette wheel. So what does negative 0.52 mean? Just pause for a second, think, what does that mean? Well, this is important, and this is really important to understanding what expected value means or what the mean of a discrete random variable means. You can't lose 52 cents playing roulette, so it doesn't mean that. What it means is, on average, over time, if I sit here and play roulette over and over again, I'm going to lose, on average, 52 cents every time I play. So if I play 100 times, I would expect to lose $52 overall. Well, will I? No, I might be one of the lucky ones that wins. But what Vegas knows is that if enough people like me play, thousands and thousands, millions and millions of times, on average, over many trials, Vegas will win 52 cents every time I play. And the average player will lose 52 cents on average every time I play. So here's the formula for expected value. And you're responsible for this. This is on the formula sheet. You'll be asked to calculate this on our test. It's quite likely you'd have to do this on the AP test. So symbolically here, the mean, mu, of a random variable x is equal to each outcome times its associated probability. And so we do that for every outcome and every probability until we get to the last outcome and the last probability. And we shorthand it with the summation symbol here. So the mean or expected value of a discrete random variable x is every possible outcome times its probability added together. It's fairly straightforward, and hopefully the examples we just gave you help. Well, let's do another example here. I've got a game. Do you want to play? So expected value is useful in deciding whether game playing makes sense or not. You have a 1/5 chance of winning $350, a 1/5 chance of winning $50, and a 3/5 chance of losing $75. Will you play, and how often would you like to play? Pause me for a minute and come up with the expected value of this game. All right, well, if you did as you were asked here, we're going to take every outcome and its probability. What are the possible outcomes here? I could win $350, I could win $75, or I could I could win $50. Or I could lose $75. The probabilities are 1/5, 1/5, and 3/5. To get the expected value, we're going to take every outcome times its probability. And so we get 70, 10, and negative 45. We sum those together, add every outcome times its probability. The formula wrote it this way, x little I times p little I. If you add those together, you get $35. So from your standpoint, is that a good game or a bad game? Well, that's a good game, because on average what that means is, on average, if I play the game many times, I'd expect to win $35 on average every time I play. Can I win 35? No, I'm either going to win 70, win 10, or lose 45. But on average, if I play it many times, I'd expect to win $35 on average. How often do you want to play? As often as you can, right? Because of the winning on average. You want to play that game every chance you get. Here's another way to make decisions. I've got two portfolios that I'm interested in investing in. A and B, with potential profits and the probability of those profits there. Which one would you choose? Pause me for a minute and come to a decision on which of these you would choose. Well, if you're doing the math here, if you can break it down, I've got every outcome and its probability one more time. So we multiply negative 1,500 times 0.2, negative 300, negative 100 times 0.1, negative 10. So I'm taking every outcome times its probability, and so on. 500 times 0.4 is 200, 1,500 times 0.2 is 300, 3,500 times 0.1 is 350. The expected value of portfolio A is the sum of all those things, which is $540. Over here, we'll do the same thing. Multiply outcomes times probability. I get negative 500, I get negative 50. Multiply again, I get positive 450. Multiply multiply again, I get positive 750, and then I get a positive 350. If you add all those up, you get $1,000. So if you're a cold calculating statistician, which portfolio? Well, you're going to invest in B because the expected value is higher in B than it is in A. Now, there's another idea here in this lesson that I want to hit quickly, which is the law of large numbers. Let me see if I can make this work properly here. Let's see. I've got two die here, and if I roll them, we did this a little bit with the casino problem in class, but if I roll these, I got a 5. So if I'd never seen dice before, I might say the expected value of 2 rolls of a die is 5. But if I roll them again, I get a 9, and now the average is 7, and if I roll them again, well, we know the expected value is 7, and there's this rule called the law of large numbers. It says if you do things enough times, run enough trials, that the average you get will approach the expected value. It will approach the true mean. And so you can see as I continue to roll these die that the average approaches 7, which is the mean down the middle there. And that's true for any discrete random variable. The more trials you run, the closer you get to the true value, the true mean, the true expected value. Right? That's called the law of large numbers. The average of the values x observed in many trials must approach mu, right, the true mean. Well, large numbers, many trials, how many? That sort of depends on the variability of random outcomes. If there's a lot of variability in your outcomes, it might take a while before it settles in on the mean. But if your outcomes lack a lot of variability, it might take a lot fewer trials to get to the mean. So the more volatility or variability, the longer you have to run your trials, and the more trials you need to run to get close to the true mean. Casinos understand this. They like to create volatility in their games because it creates excitement. So they balance the psychological idea of big winnings and big losings with the long-term probability that you're either going to take your money. So the casinos live off the law of large numbers. Now, the last thing in the lesson here is there's also a variance for discrete random variables. And we're just going to give you the formula for that. So we're measuring the variability of outcomes. We've talked about standard deviation before. Standard deviation is a measure of variability about the mean. So recall that we have this symbol for variance, sigma squared, and we have this symbol for standard deviation, sigma. So the variance is the square of standard deviation, or standard deviation is the square root of variance. You're responsible for this formula. You'll have to execute this formula on a quiz or test in class. Notice what's happening. We're taking every outcome minus the mean, so there's distance from the mean. For variance, we square the difference and multiply by probability. We do that for every outcome, every value. Dot, 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 up to the last value. And then we sum those things together. So the formula for variance is here, the sum of every outcome minus the mean squared times the probability of that outcome. To get to standard deviation, we simply take the square root of the variance. So again, it's a measure of distance from the mean. It's every outcome, this is standard deviation, minus the mean squared times probability. Take the square root of that and we get the standard deviation of the discrete random variable. In the next video, we'll see some examples of calculating that, but for now, just make note of the formula. That formula will be given to you on your formula sheet, and you're responsible for being able to execute